Hi everyone, in this video we are going to discuss the longest increasing subsequence problem. Before solving this problem, let's go over the key terms to understand what is the longest increasing subsequence. What is a sequence? A sequence is an ordered list. The length of a sequence is the number of elements in the list. For example, 6, 3, 4, 5, 7, 1, 11. What is a subsequence? A subsequence of a sequence can be generated by selecting some or all of the elements from the sequence while retaining the order of the sequence. For example, 3, 5, 1, 11 is subsequent to the sequence 6, 3, 4, 5, 7, 1, 11. Now, what is an increasing subsequence? A sequence A1, A2, A3 to AN is increasing if A1 is less than A2 and A2 is less than A3 and so on. For example, one possible increasing subsequences of the sequence given above is 3, 5, 7, 11, and the longest increasing subsequence is 3, 4, 5, 7, and 11. Now that we know what is a longest increasing subsequence, we can look into finding the longest increasing subsequence of a given sequence. We will look into two approaches to solve this problem. The first approach is the less efficient approach, which is the naive recursion enumeration. This method generates all the possible subsequences of the given sequence. After obtaining all of those subsequences, we would go through them one by one and determine whether the subsequence is increasing. Let's look at an example. Here we have a sequence 6, 3, 5, 2, 7. We then generate all of the possible subsequences of this sequence by choosing to include or not include the last number of each generated subsequence. In the first level, we choose to include or not include 7, the last number of a given sequence. In the second level, we choose to include or not include 2, the second to last number in the given sequence. In the third level, we choose to include or not include 5, the third to last number in the given sequence. We continue doing this process to generate all of the possible subsequences. After we obtain all of the possible subsequences, we check if each subsequence is increasing. The color green signifies that the subsequence is increasing, and red indicates that the subsequence is not increasing. This approach would take O of n times 2 to the power of n runtime. 2 to the power of n comes from the fact that there are 2 to the power of n subsequences of a sequence, and O of n is the time taken to check if a given sequence is increasing. The next approach is the backtracking approach. This approach is also where dynamic programming will come in. Here's the major idea of the backtracking approach. So we don't really need to generate all of the subsequences and then check if they are increasing. Really, we need to only look at the increasing subsequences, and we don't have to wait until we generate all of the possible subsequences. Let's say the sequence is 6, 3, 5, 2, 7, 8, 1, and we want to construct one of the increasing subsequences. Well, starting from the back of the sequence, we know that if 1 is in the subsequence, the previous values cannot be in the subsequence. If we skip 1 and then decide to include 8, we know that all the values that come before must be smaller than 8. Hence, we can progressively check to make sure that a subsequence is increasing by having another variable that keeps track of the smallest or the leftmost element in the subsequence suffix. Hence, we would still have two cases. The first case is when the longest increasing subsequence does not contain A of n. This means that the longest increasing subsequence of the array A from 1 to n is actually the longest increasing subsequence in array A from 1 to n minus 1. The second case is when the longest increasing subsequence contains a of n. This means that we have to find the longest increasing subsequence in A, where each number in the sequence is less than a of n. This suggests that for the second case, a more general problem is LIS smaller of a from 1 to n and x, which returns the longest increasing subsequence in A, where each number in the sequence is less than x. So let's look at an example. Sequence A equal to 6, 3, 5, 2, 7, 8, 1. In the beginning, we initialize x to infinity and the current sequence to empty. Similar to the last approach, in the first level, we choose to include or not include 1, the last number of the given sequence. If we choose not to include 1, the problem is exactly the same as the naive approach. The difference is that if we choose to include 1, we must also set x to 1 to ensure that from now on, we will only include a number smaller than 1 so that our subsequence is increasing. In the second level, we choose to include or not include 8, the second to last number in the given sequence. This layer's first and second node is the child of when we chose not to include 1 in the longest increasing subsequence, and so x is still infinity. This means that we still have the choice to include 8 in the sequence since 8 is less than infinity. On the other hand, for this node, we chose to include 1 in the sequence in the previous level. Since 8 is not less than 1, we can include 8 in the sequence. In the third level, we choose to include or not include 7, the third to last number in the given sequence. Since x is still infinity, we have the option to include or not include 7, since 7 is less than infinity. Here, x is 8 and 7 is less than 8, so we still have the option to include or not include 8. We continue this process until we reach the first number in the sequence. So the good news is that doing this optimization means we don't have to check if the subsequence at the end of the recursion is increasing. The bad news is that there could still be a lot of possible subsequences. In fact, if the input sequence has length n, there are still 2 to the power of n subsequences. Hence, the worst case time complexity is still all of 2 to the power of n, which is not ideal. Now let's look at the dynamic programming approach. Let's look at our recursive function from our backtracking approach. Notably, let's realize 2 things. First, the variable x can only be one of the n values in the input sequence. Second, the input sequence can only be a prefix of the original input. Therefore, there are only n input prefixes that a can be. Hence, there are O of n squared distinct subproblems, as we can see that there can be up to n prefixes and n different number for x. Together, we have O of n squared subproblems, as we have 2 n inputs. In theory, if we memorize the recursion, each subproblem would only take all of 1, as we can soon see that each call is just a call to another recursion, or just a max function. So the running time would stay the same at all of n squared. Now we will see how we can remove all recursive calls by memoizing and evaluating in good order. We will soon understand what I mean by good order, and this is where dynamic programming comes into play. Let's define a problem again in a manner that will facilitate memoization. Let LIS of I and j returns the length of the longest increasing subsequence in A from 1 to I, consisting of numbers less than A of j. For the base case, when I is equal to 0, the sequence we are evaluating is empty, and so the longest increasing subsequence is always 0, regardless of the x input. As for the recursive case, If a of I is greater than or equal to a of j, then we have to compute LIS of I minus 1j because we can't include a of I in the sequence because otherwise the sequence would not be increasing. So j remains the same and we move on to the next index by passing in LIS I minus 1j. If a of I is less than a of j, then we can choose to include or not include a of I. If we choose to include a of I, then the length of the longest increasing subsequence would increase by 1. So we add 1 and change x to I, and then move on to the next index by passing in I minus 1. If we choose not to include a of I, then j remains unchanged, and we move on to the next index by passing in LIS I minus 1j. From these relations, we can see that each LIS ij rely on LIS calls with previous input I minus 1j and I minus 1i. So if we are able to evaluate those inputs first and store the results of those computations to be lookup, each subproblem would only take constant time. This means that we would be able to fill the 2D array in the bottom-up order from I equal to 0 to I equal to n. It does not matter if we fill in the 2D memoirs array from left to right or right to left, since the entire row above the current row would have already been filled. And this is what I mean by the good order. Now let's fill in the 2D array. We will add a column for x since x starts out at infinity and any value can be added to the recurrence when x is infinity. Also notice that the lower triangle does not need to be filled. That's because x, the column values, can only be a value, let's say 6, if 6 is not in the input prefix. X only becomes a particular value when we assume that value is taken out from the input prefix and added to the longest increasing subsequence suffix. Filling in the first row, this is our base case. When I is equal to 0, the prefix sequence we are evaluating is empty, and so the longest increasing subsequence is always 0, regardless of the x input. So we fill in the first row to be all zeros. For the other rows, we check if a of I is less than a of j, and follow the step defined in the recursive function. After filling up the 2D array, our answer is simply in LIS of n plus 1, which in this case is 4. And that's the basic derivation of the longest increasing subsequence problem. We start from a recursive problem and optimize it or backtracking. Once it is optimized, we can look to see how many subproblems there actually are and if we can order the calculation of the subproblems to make the computation more efficient. Thank you for watching, everyone.